We got another a really big supply chain attack going on right now, and it's still ongoing, and it's spread from the NPM also to the Python ecosystem. So maybe right now, don't install any NPM or Python packages. And make sure your system is set up securely in general. I got another video on that. I'll share a link below, and I'll get back to it here in this video too. But first, I want to give you some details on what is affected and to find out if you're affected. It started with the TanStack packages, TanStack Query, TanStack Router, TanStack Start, and so on. Yesterday, May 11th, in a pretty short time frame, a couple of malicious packages, or actually all TanStack packages, were published with malicious versions. And it was contained quickly. Within 20 minutes, in the end, it was detected and contained quickly. But all these malicious packages have been published in that time frame, or in that short time frame here. And then it continued spreading, and it still is spreading. It spread to the Mistral packages, which, only have 4 users, but still that was affected because this malware acts as a worm and steals data, steals credentials, also potentially yours if it is installed on your system. I'll get back to how to find out if you're affected in just a second. But it continued spreading to more NPM packages because that is the idea behind it, and then even into the Python ecosystem. And that's happening right now. This is just a few hours old here, 2 hours at the point of time where I'm recording this. Now, how do you find out if you're affected? If you installed any TanStack package yesterday evening, in my case here in the German time zone, you must consider yourself affected if you installed it around that time. Keep in mind that is UTC, so you have to translate that to your time zone. In that time, then you must consider yourself affected. But since it's spreading to the Mistral packages, to many more JavaScript packages, more than I could list here, you also must consider yourself or your machine affected and compromised. And I'll share links to these posts below so that you can dive deeper and see the full list of all these affected packages as they have been published. But as mentioned, it's still ongoing, so maybe don't install anything right now. There also are indicators of compromise. You want to look for certain file hashes, SHA hashes, for the router init.js file. I'll also link this post below. And if you have a way of monitoring which network request happened on your machine, you want to look for outgoing traffic to this URL, which would be another clear indicator that data has been exfiltrated from your system. What does compromised mean in detail? It means that this malware does in the end 2 main things. The first important thing it does is it harvests data. It looks for NPM tokens, GitHub tokens, AWS credentials, other secrets. So it scans your system for typical locations where you store credentials and secrets, and it collects them and sends them off to this URL I showed you. So it steals these secrets, but it does not just do that. As I mentioned, it acts as a worm, so it also uses these GitHub tokens that were stolen, for example. It uses them and the NPM tokens to publish more compromised packages. If you're the maintainer of another package, or if maybe you have a CI/CD workflow that ran in that time frame and that depended on some TanStack packages, then in that CI/CD workflow, the compromised TanStack packages have been pulled in. The malicious code may have executed in there, and then in that workflow, so not on your machine, but in that workflow, it also could steal certain credentials to publish a malicious version, a compromised version of the package your CI/CD workflow was trying to build. So that is how it spreads. As I mentioned, it acts as a worm. It's using these stolen credentials and tokens to publish more compromised packages. And that is how it spread to Mistral, and then also other JavaScript packages, and then even into the Python ecosystem. And this is where we are right now, and it still is spreading for all I know. Now, how can you protect against that? I created a video about that on my other channel, Academind. I'll also link it below. the short story is you want to make sure that you run your code or that you do your development not directly on your root machine if possible, but instead in some virtual machine, in a dev container, something like this. You don't want to store raw secrets on your machine. I mean, for AWS, for example, you want to use their single sign-on approach instead of storing IAM credentials on your machine, for example, and use similar techniques for other services you may be using. In addition, you also want to consider using services like InPhysical or Doppler for storing your secrets in the cloud and not on your hard drive, not in .env files. That is something you may want to do. And again, I talk about stuff like that in that video. And you also want to use package managers and configurations that allow you to configure stuff like the minimum release age, like Bun allows you to do. In the bunfig.toml file, you can set a minimum release age, which makes sure that even if you do run bun install, you only install packages that are at least X seconds old, X days old in this case here in this example. Now, PNPM has a similar feature. The latest versions of NPM have a similar feature. Again, I covered that in that other video. And if you do use something like Bun, or if you have the right configuration for NPM, but Bun does it as a default, for example, then it also blocks the execution of, for example, post-install scripts, so of lifecycle scripts of those packages you're installing, which gives you another security mechanism because that malware typically relies on such scripts being executed on your system. So using a secure package manager and or secure configuration for that package manager, running your code in a virtual machine or in a dev container, and not storing plain secrets on your system, that is what you want to do in general, but now maybe even more, because those attacks like these here, will just become more serious. And we'll dive into how that attack worked because it's really interesting. But of course, we're having more of these. I create a video like this almost every month now, or maybe even more frequently, because for one, I believe they are easier to pull off now in the age of AI. It's easier to analyze the packages or the dependencies you want to affect and analyze their source code or their CI/CD setup for potential attack vectors. That is what happened here for TanStack. It's not as if a maintainer's machine was affected, but instead it was the TanStack CI/CD workflow that has been attacked. And I'll get back to that. So it's easier to look for vulnerabilities with AI. It's easier to write code, malicious code included, of course. And at the same time, we got that explosion in software. We got more software being written than ever before. So there are more targets out there, including many targets that maybe don't care too much about security. So that makes those attacks more interesting too. Now, how did this all start? It's really interesting. As I mentioned, not a novel approach, not one we never saw before, but still quite elaborate. The TanStack team published a post-mortem, an article where they explain how the attack happened, and I'll link that below too, but of course I'll give you the summary here, because in the end, this attack here relied on three main steps, which I'll explain in detail. A pull request target pawn request pattern, I'll explain what that is, then GitHub Actions cache poisoning across the fork-based trust boundary, and runtime memory extraction of an OIDC token. Okay, what does that all mean? Again, you can read the article for all the details, but let me give you the summary. And let's start with the pull request pawn request pattern. What is that? In order to understand that, we have to understand that GitHub Actions is, of course, the CI/CD solution, the CI/CD product by GitHub. And I do have a course on GitHub Actions too, by the way, if you want to learn how to set up GitHub Actions, how to use that product for CI/CD tasks, how to publish your packages or your website, and so on. Now, like all CI/CD workflow tools, GitHub Actions relies on events that trigger workflows because, of course, CI/CD is all about doing something in an automated way. For example, releasing your website, publishing, deploying your website in an automated way when you push to the main branch, for example. So you have various events that can trigger a workflow, and push is one event, for example, so that you can say, okay, if I push to the main branch, for example, you can filter for different branches. Then I want to execute certain tasks. I want to install my dependencies. I want to build the project. I want to upload it to my server. That is what you could do. Now, one other trigger is pull request target. This trigger activates if there has been a pull request opened for your repository. And that, of course, means anybody can fork your repository, do something in there, push something in their fork, and then open a pull request with your repository. And that would trigger this workflow. Sounds dangerous? Well, it kind of is, and it is what started this attack. There also is the pull request trigger. So I talked about pull request target before, but we also have pull request, which works in the same way. But pull request then runs the CI/CD workflow in the context of the forked repository. So whatever malicious may be going on in there, it happens in the forked repository, not in the base repository. So this is not a problem. Pull request target, on the other hand, runs in the context of the base repository. And that, of course, is potentially dangerous. It's potentially dangerous because anybody can open a pull request. And of course, what happened in this case here for the TanStack attack, in that pull request, in that fork, the attacker included the malicious code, the worm code, the malware in the TanStack repository, in the fork of it, but it included it in there. Then the attacker opened the pull request, and that led to pull request target being executed. And then, as mentioned, that then spins up a GitHub Actions runner, and it then runs in the context of the base repository. What does this mean? This does not mean that the attacker gets access to the base code or can merge the malicious code into the repository, but it means that, for example, the cache that's being used in there will be shared with subsequent GitHub Actions executions that stem from the base repository, potentially from totally different hooks or event triggers like the push trigger. The next thing that happened was the cache poisoning. But what does this mean? Well, the attacker added code to their fork that would make sure that when the GitHub action ran for that pull request target trigger, it would run a command, the hash files command, which is supported by GitHub Actions, to store something in the GitHub Actions cache. Now, what is that cache about? The idea behind the GitHub Actions cache simply is to speed up those GitHub Action workflows. So you can, for example, hash dependencies. The idea being that if a dependency your package depends on hasn't changed, why would you go through the entire installation process again? That just takes time, and time is money because you're built for the runtime of your GitHub Action workflow. And of course, you don't want to have workflows that take forever. So in most workflows, of course, for example, when building the TanStack packages, you install the dependencies of the TanStack packages, and then you do the build step and build your TanStack package. Again, if those dependencies of TanStack haven't changed, why reinstall them? That's the idea behind caching, and that makes sense, of course. The problem is, since that pull request target GitHub Actions execution and other GitHub Action executions, like the ones for the push trigger, share the same context, they share the same cache, and that is where cache poisoning comes in, because the attacker was able to cache a malicious version, or to put that malicious code into a dependency of TanStack, so to say, and cache that. So then the attacker just had to wait for a normal GitHub Actions workflow to run for the TanStack packages, so for some maintainer to push some code, and then that other GitHub Actions execution would reuse the same cache that was set up by the malicious execution before, and would now pull in the prepared poisoned cache, which included the malicious code. So that is how the malicious code got from the fork into the normal GitHub Actions execution for a normal push by a normal maintainer who has not been affected by any malicious code. That is how the cache was used as a transport vehicle between these two GitHub action executions in the end. And then as a third step, once the malicious code made it into a regular execution of a TanStack CI/CD workflow, because of that push event, it stole a short-lived NPM token, an OIDC token in the end, to publish a malicious version of the TanStack package. Now, what am I referring to here? NPM has that feature which is called trusted publishing, which in theory makes publishing NPM packages more secure, because there are roughly two ways of publishing a package to NPM, you could say. One is that you create a token with your NPM account, and you use that to publish new versions of your package. The problem is if that token gets stolen, anybody can publish a new version of that package. To ramp up the security, there is this trusted publishing process where NPM says, no, you can't publish packages from your machine. You have to go through one of these trusted providers, GitHub Actions being one of them. And there is a trusted publishing integration for GitHub Actions, which you can set up. And then as part of that trusted publishing process, a short-lived publishing token will be retrieved or will be requested. And then that short-lived token will be used for signing that new package version that is being published. So in theory, the idea is that the token is hard to steal because it's not on the machine by any maintainer. And in addition, it's short-lived. Even if it were stolen, it's not active for very long. The problem, of course, just is if the code that runs in the CI/CD workflow that is requested that trusted token, if that code has been affected, then that malicious code has access to this brand new short-lived trusted publishing token. And that is what happened here. So that malicious code abused this token or used this token to then publish a new version of the TanStack package. Now, interestingly enough, this attack actually failed a bit because it did get that trusted token and it did use it to then reach out to the NPM API to publish a new version of the TanStack package that included this warrant, that included the malicious code. But it actually ended up in a GitHub Actions workflow that failed to complete because there was something wrong in the code that was pushed to CI/CD. So if the attackers would have paid attention to run their attack at a point in time where valid code would be pushed, then of course this workflow would have completed and they would not have had to rely on publishing a malicious package manually by reaching out to the NPM API, but instead they could have injected the malicious code into this workflow as they did, let this workflow finish successfully, and then a compromised version of TanStack would have been published whilst looking very valid because it was a normal push by a maintainer and the workflow finished successfully. The way this attack worked, because that workflow did not finish successfully, made it a bit easier to catch what was going on by an external contributor here in the end, because you could see that a new version of the TanStack packages was published, even though the GitHub Actions workflow failed, so no new version should have been published. So you could see a mismatch there, which made it a bit easier to detect this attack, which is kind of, one part where the TanStack maintainers and we all got lucky. Nonetheless, a pretty elaborate attack, as you can probably tell, that worked totally without compromising anybody's machine. And even though it was caught quickly, it did serious damage because, as I mentioned, it is still spreading. And that was a long episode about all that, I know, but I really want to emphasize, you have to work on making your system secure. As I shared before, as I share in this video, you want to make sure that you reduce the danger of being affected. This attack, again, was caught quickly, and yet it is still spreading. So it's not over yet. And it is possible that not all attacks will be caught that quickly in the future. As mentioned, they got a bit lucky here. It could have been harder to detect this attack. So then maybe the damage would be even greater, but it's already pretty large here and it's not over yet. And we'll see more such attacks, I'm sure, because I mentioned the attack surface is getting bigger and more interesting. There are more people writing code, lots of people that don't know what they're doing, and AI helps with running such attacks. So yeah, this is what's going on right now. If you don't have to, maybe don't install anything, double check your setup, and you find all the links below if you want to dive deeper, if you want to see the full list of affected packages and so on.